This is section 10.1 sequences. In this session, we will talk about the geometric sequence only. Let's check. A sequence with the form C times R to the power of n, where C and R are non-zero constant, is called a geometric sequence. Let's check the expanded form, C times R to the power of n, and we're assuming, of course, that we're starting from 1. Then we have these terms. C, the first term is C R to the power of 1, C R to the power of 2, C R to the power of 3, and so on. We may notice that in order to get the next term, we will take the previous one and multiply by R, because it's just R squared, R cubed, R to the power of 4. Then we may define the ratio. For instance, let's take the second term, divide by the first one. The second term is this one. And when we cancel out, we have R. Or we can take the sixth term and divide by the previous one, which this is R to the power of 6, R to the power of 5. We can cancel out this R. Okay? That means each term is R times the previous terms. And that ratio, saying in general a sub n over a sub n minus 1, because here we will have a term C times R to the power of n minus 1. We remember that order. Or if we like even one before, n minus 2. Okay, and so on. That means these terms can go here. Or I can even define the next term, n plus 1. Okay, and so on. But when we take this general ratio, a sub n over a sub n minus 1, it's equal to R, and that R, that number R, we do call common ratio. Right? That's the common ratio because we getting common number, the same number, R, R, R. If we change a little bit algebraically, we get kind of like a definition of the nth term, which is of course defined as a one term, like the previous term times the common ratio. Okay, this is in general the definition of the geometric formula, geometric sequence. One thing it's important, in order to recognize a geometric sequence from the list of different sequences, we may always look where is the n. If n is placed in the exponent, like an exponential form, only. Yeah? We cannot have n's somewhere else in the formula. If the number is taken to the power of n, the constant non-zero number is taken to the power of n only. That's the geometric sequence. Okay, the main question now is, we have to figure out what is the value of this common ratio. What is the value of R? Because everything depends on R. What is the value of R that will give us convergence? Or, of course, otherwise divergence. We have to find out when the geometric sequence converge and when diverge. And let's start investigating all of the numbers R. The example 1a. For what values of R is the sequence R to the power of n convergent? And I will just assume that constant C is 1, because it's not the constant C, it's not affecting the convergence, only that part R to the power of n. Okay, and I would like, did I start? Okay, because I started, that's supposed to be okay. That's me. What we will do, we can use the next slide, but looking maybe this will be, this is just for just the visual like help. We will take couple of values of R. We will take we will check 0 and 1, and actually I would like to check -1 also. Okay, that means we will check what is happening with the sequence if R is 0, 1, and -1, okay, because we may have negative, and then we will check what is happening with the sequence if if R is between 0 and 1, what is happening with the sequence if R is between -1 and 0, and what is happening with the sequence if R is greater than 1 and R is less than -1. Okay, that we will take all of the numbers from the number line. And let's start. I think I got ready for 1 and 0, which theoretically we're not letting R to be 0, but let's just check it. And I also wanted to check -1. Okay, let's see 1. It's actually not really complicated, because when we will take a sequence 1 to the power of n, 1 to the power of 1, 1 to the power of 2, 1 to the power of 3, 1 to the power of any number is 1. Limit 1 to the power of n is constant 1. So we may say is convergent to 1. When R is 1, the geometric sequence is convergent. Converges to 1. Because it's just 1, constantly 1, 1, 1, 1. Okay, that's good. We did 1. Now 0. Similar situation. 0 to the power of 1, 0. 0 to the power of 2, 0. 0 to the power of 3, 0 to the power of 4. It is 0. It means when R is 0, which we will avoid this. But just here, just in case if we end up with this situation, this limit is 0, the sequence converges to 0. Okay, that means 0 is giving us, okay, and as I said, let's investigate -1, limit -1 to the power of n at infinity. I wonder what is happening with this. -1 to the power of n. Looks like a geometric sequence, because n is placed in the exponent. -1 to the power of 1, -1 to the power of 2, -1 to the power of 3, -1 to the power of 4, and so on. We remember this. I can draw first term, second, third, fourth, fifth, sixth, and so on. The first one is taken to the power of odd number is -1. That's the number of terms. A sub 3, 4, 5, 6, 7. And then the second term is +1. And then -1, +1, -1, +1. The terms like oscillate, never approach one finite number. The limit basically does not exist. Sequence is divergent. Okay, that means 1 is good, 0 is good, -1 is not, because we have to figure out all of the values of R. Okay, now let's take that small sub-interval between 0 and 1. Let's see what's happened. Because for all of the numbers between 0 and 1, all of the values of R, the situation is the same. I can pick a number, 1/2. Okay? For instance, 1/2. Limit of 1/2 to the power of n as n goes to the infinity. We probably explicitly, we can get this limit, but I would like to list the terms. Yes, 1/2 to the power of 1, 1/2 to the power of 2, 1/2 to the power of 3, 1/2 to the power of 4, and so on. Okay, so we can see what is happening. Actually, I can even indicate the terms are getting smaller and smaller. 1/4, 1/8, 1/16, 1/32, 1/64, 1/128, and so on. The terms are approaching 0. It's basically 1 over big number. We remember how we compute 2 to the power of n. At infinity is infinity, 1 over infinity, or we maybe, it's better to say 1 over big number, is a small number. Sequence with the common ratio being any number between 0 and 1 is convergent to 0. Converges to 0. That means the terms are getting smaller and smaller and smaller, which is good. And maybe just in case to have another look at this, 1, 2, 3. Okay, that's the terms. And the first term is 1/2, and then 1/4, 1/8, 1/16, and so on. I can possibly draw, we remember, a function. One thing that maybe I can just say that all of the terms are all of the terms are above 0, but never all above 0, but less than 1/2 or equal to 1/2. And that means between 0, all of my red dots, which represents the terms of the sequence, the red dots, they are between 0 and 1/2. Then we can say later, we will also have this terminology, this sequence is bounded, limited by 2 numbers. Okay, but our main question is to find convergence. All of the values of R between 0 and 1 will give us convergent, and it's convergent to 0. Okay, another subinterval. What about the numbers between -1 and 0? For instance, -1/2. Limit of -1/2. The common ratio is negative, but still fraction. Let's expand. What we can do, we can write that our sequence is defined as a -1 to the n, and when we expand this, the first term is -1/2. The second term is +1/4, -1/8, because the power is even odd, then we have alternation. 1/16, -1/32, and so on. The general formula is this. And we have to figure out, are these numbers approach one finite direction, one finite number? Yeah, you may try to answer. If we will plot this, then we can see a little bit more clear. The first term is -1/2. First, that's the terms, 1, 2, 3, 4, -1/2. Then +1/4, -1/8, +1/16, -32, -1/32, +1/64, -1/128, and so on. Let's connect this, because then we will see. Of course, we're just looking at okay, because the magnitude, the absolute value of these terms are getting smaller and smaller. But original formula, original sequence is alternating through the positive, negative. It's not, the numbers are still approaching 0, because we can nicely see that snake, that green line, it's getting closer and closer to 0. So we can definitely say this limit is 0. This sequence converges to 0. In order to compute the limit explicitly, we can use this property. We can compute a limit of absolute value of the formula. And if the absolute value is 0, then the original sequence also has the same limit, 0, meaning that it's convergent to 0. Let's do this. Limit as n goes to 0 to infinity. I can also split this. -1/2 1 to the power of n and 1/2 to the power of n. That's the same thing, -1. When I combine this, it will be -1 times half, -1/2 to the power of n. Now, taking absolute value, we will change the limit. -1 to the n will become +1. 1/2 to the n is always positive. It stays the same. And we know that this 1/2 to the n, 1/2 to the n, because 1 to the power of n is always 1. 1 over big number is a small number, but this is absolute value. Since the absolute value is 0, the original sequence has also limit 0. Limit of -1/2 to the power of n as n goes to the infinity is 0. Sequence converges to 0. It's getting closer and closer. Right? That means this interval also gave us convergence. Yeah, we will put together all of the values. Now we can say that from -1 to +1, all of these fractions, yes, all of these fractions less than 1 or greater than -1, actually, if this is the common ratio value, the sequence is convergent. Also 1 and 0 is giving us convergence. -1, no, -1 was like oscillation. Okay, now we have the other parts. We have to look at the number greater than 1. For instance, 2. For some reason, I like that 2, 1/2, -1/2, 2. Okay, limit of 2 to the power of n at infinity. Of course, we can say right away, it's a huge number, 2 to the power of n. As n is huge, it's a huge number. The limit does not exist as a finite number. Sequence is divergent. Okay, and no even confusion, because it's 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 5, and so on. 2 to the power of n is approaching infinity. This is just the exponential function. Where we are, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, 4, because they're growing really fast, is, if we will start with 0, 2 to the power of 0 is 1, but not always. We know that occasionally we can start. That means it's definitely approaching huge numbers. This interval, these values, will give us divergence, not a convergence. Sequence is divergent. Okay, and then the other part, actually, let me just check. Okay, we do have, yeah, we have graphs, good. Now, the other one, all of the numbers less than -1, like a huge number, but negative. I will, of course, pick -2. Limit as n goes to the infinity, -2 to the power of n. I know that you probably know the answer, but let's look at the expanded form, let's look at the graph, and then we can figure out -1 to the power, -2 to the power of n, -2 to the power of 1, -2 to the power of 2, -2 to the power of 3, -2 to the power of 4, and so on. Yeah, the numbers alternate. The numbers alternate, but they know the absolute value of it is not going smaller and smaller. It's actually 2, 4, 8, 16. We may notice that each term negative, like the first term is for the first, then we have like the picture, -2. The first term is -2. Actually, let me ignore the scale because the numbers, let's pretend that that's -2. And then +4, -8, +16, -32, +64. That means these numbers, how can I can maybe connect them like this, right? They will go to the infinity, like the positive infinity, every other number, and every other number will go to the negative infinity. They definitely, these terms of this sequence are not approaching one finite direction. I can't even say positive or negative infinity because it's like alternating. So yeah, this definitely, the sequence is divergent because we do not have one direction. Explicitly, we may also, how we can split this -1 to the n and 2 to the n. That's the same thing. Also, it's helpful to know this because -1 times 2 and common exponent n. And we may also apply the absolute value, but I don't think it will work because when we apply absolute value, the -1 to the n will be +1. 2 to the n is always positive. It will stay positive. And 2 to the n, exponential form, 2 to the 2 at the big numbers is a big number, it's infinity. The limit does not exist. Yeah, then adding like getting back to the -1 to the n without the absolute value, we will kind of have, I can write this limit, it will be not informal, it will be like informal. But one more thing, first of all, we are not allowed to use this property because if the absolute value is not 0, then we have to just look at different things. And we did, we have the expanded form, we have the graph. But this one, I can definitely say the limit does not exist. But what I'm thinking, it is like positive, negative infinity. Yeah, because we can see it's going like 4, 16, 64, and so on, like the even powers, and the odd powers, -2, -8, -32, and so on. And that means going like in both directions, but of course it's even like not a finite number, infinity. So, but this is really informal. We know that is limit undefined, the sequence is divergent. Okay, we analyzed all of the numbers. I can possibly come back to this, that we can see. If we taking numbers from this, convergent, all of these numbers are giving us divergence, and also convergent is for r equals to 1 and r equals to 0, which we not really, we prefer, we will have non-zero number, but I can actually say 1 and 0, but not -1, right? Because -1 is giving us oscillation. Convergence, all of the blue numbers are giving us convergence. And I have a little bit more professional summary. That's the summary. The sequence r to the power of n, yeah, the geometric one, is convergent if r is between -1 and 1, including 1. Divergent for all of the other values of r. And we notice also that if the r is between these numbers, it was convergent to 0, just for r being 1, convergent to 1. But we can always analyze. Okay, that means it's worth to remember one more time, if the common ratio is between -1 and 1, the geometric sequence is convergent to 0. If it's 1, it's convergent to 1. But if it's outside this interval, it's just divergent. And I have another summary. You can look at this. We put this. I add C in this case, but C is positive, because if C will be negative, then we still hold the convergence divergence conditions, but we will go like in a little bit different terms. We will have different terms of the sequence. Okay. And let's analyze. I have exercise number 2, 2, 4, 5 problems. Let's just get the limit. All of them are the sequences that I just wrote in the limit. Okay, 5 to the power of n. Of course, the limit is infinity, or we will say the limit does not exist. The sequence diverges. Negative 5 to the n, also the limit is like positive negative infinity, but I will say does not exist. Diverges. 1/5. 1/5 is from that interval. We will have 1 over 5, 1 over 25, 1 over 125, 1 over 625, and so on. 1 over big number, 1 over big number, as of course n goes to infinity, is 0. Converges to 0. Okay, negative 1, negative 1/5 to the power of n, also is convergent to 0, but through this alternation. Negative 1 over 5, positive 1 over 25, negative 1 over 125, positive 1 over, I believe, 625, yeah? 5 to the power of 4. Yeah? It will be like this kind of like a snake, above, below, above, below. And if we will take absolute value of this, the limit will become 0. That means, yes, this is definitely, limit is 0. Convergence sequence is convergent to 0, because we know that that common ratio is negative 1/5. Common ratio is positive 1/5. Common ratio is outside that interval. I'm just writing. And this one, let's figure out what is the common ratio. A little bit of algebra. We have 5 to the power of 2 and 6, and everything is taken to the power of n. 25 over 6, that's the common n. That's the common ratio. This is number greater, of course, greater than 1. It will be infinity, or if we prefer DNE. The sequence is divergent. We can also look at the growing rates. Like we remember limits at infinity. This is 25, yeah, a little bit tricky. 25 to the n versus 6 to the n. 25 grows definitely much, much faster. Numerator is winning, the answer is infinity. In this case, we will say that the limit does not exist, the sequence is divergent. Okay, another one. Typical question. Determine whether the following sequence converge or diverge. If the sequence converge, find its limit. Okay. You may figure out what is the common ratio. Let's actually figure out what's the common ratio. 3 to the power of 2, 4. This is the number which is taken to the power of n. 9 over 4. Because we always have to combine all of the quantities taken to the power of n. And we can use this exponents property. The common ratio is actually greater than 1. The sequence is divergent. I can say 9 to the power of n, 4 to the power of n. You will see that is infinity. And the sequence is divergent. We have limit, we have the value of the common ratio, we have everything. Okay, another one. Now we have 2 to the power of n minus 1 over 3 to the n. Definitely, this is geometric sequence, because I didn't even assume that because we practicing the geometric. The common ratio I really would like everybody to see that is 2 over 3, because I see a number 2 in the numerator taken to the power of n, and I see 3 in the denominator taken to the power of n, 2/3. Common ratio is less than 1 in this case, and of course, it's from that interval, the sequence is convergent to 0. Let's maybe, we will say 2 to the n, 2 to the -1, 3 to the n. And you can also look at the growing rates, 2 to the n versus 3 to the n. Just 2 to the -1 is just the coefficient. I can say 2 to the -1 is 1/2. Yeah, if we like this way, so in 2 to the n, that's the leading function, 3 to the n leading function. Of course, 3 to the n is winning. If the denominator winning, the limit is 0, but maybe one more, I can combine this. And this is 1/2. The common ratio, now we can see the common ratio, but we saw it right away. 2/3 less than 1, these numbers will go to 0. Like 2/3, 4 over 9. Oh, what's that? 8 over 27 and so on. Definitely the numbers are getting smaller and smaller and smaller. They are approaching 0. Yeah? You don't have to write everything, but I'm writing everything. Yeah? For you to pick whichever way, if you like the growing rates or if you like looking at the common ratio, but the common ratio is quite important to know, to figure out almost right away. Looking at the geometric sequence, like what is the common ratio? If I will show you this blue loop, you will tell me 2/3, okay? Because 2/3 is taken to the power of n. That's the only number that is taken to the power of n. Okay, sequence is convergent or converges to 0. It's approaching 0. All of the terms, of course. And maybe let's just find out the first term, just in case. If we have to find out the first term, a sub 1, in this case, we will substitute instead of n, 1. 2 to the power of 0 over 3 to the power of 1. 1/3 is the first term. Okay. Of course, if we have to find the second term, we will plug in 2 for n. Okay, I have another one. I have a couple more and we will finish the session. Another sequence. We will look at this for a few seconds and we will figure out that n is placed in the exponent only. And that's, the conclusion is, this is the geometric sequence. Okay, geometric sequence, what is the common ratio? The common ratio is 5, 4 times 3, because that's the numbers taken to the power of n, 5 over 12. The common ratio is 5 over 12. This is less than 1, greater than -1. The sequence is convergent to 0. Converges to 0. And we can see how nice we are. So we master this, the skills of the geometric sequence. Okay, but let's figure out, because probably when somebody see, oh, how we know right away, but we can see 5, 4, and 3, of course, respectively in the numerator and denominator. Okay, that's how we can figure out quickly. But let's maybe combine them together. If we have to look at the limit, what I will do 5 to the n times 5, 4 to the n, 4 to the -2, and 3 to the n. And maybe that form will tell me 5 to the n, leading function, and 4 times 3 to the n. I can combine this. And this will stay 4 to the -2 is 1 over 4 squared. And let me write this one more. Then we can look, this is the leading function, 5 to the n, 12 to the n, and 1 over 16. And you will say right away 5 to the n versus 12 to the n. 12 to the n is in the denominator, is growing like faster, the relative growing rates. This is definitely 0. Or if you like, you can still combine this 5 and 12. Then we can see this is that common ratio that we knew it right away. And 5 divided by 1/16 means 5 multiplied by 16, because we have to flip it. Doesn't matter the constant, the main thing, the r to the power of n. This is less than 1, this will approach 0. 5 times 16, I think is 80, but we can leave it like this, right? Because that's not constant, it's not important. The n, the infinity makes sense. And we have to focus on this. Okay, converges to 0. You may do the limit. Again, you may pick part of this, but if you understand what we did at the beginning, that's great. I have 2 more. Another sequence. -1 to the n, 3 to the n over 7 to the n. I notice that all of the n's are placed in the exponent. Then I know that this is geometric sequence. And now I'm looking at the common ratio. Common ratio r is a number, I mean the entire quantity taken to the power of n. And what I see -1, 3, and 7. -1, 3, and 7. That's the common ratio. And this is number also between -1 and 1. The sequence converges to 0. Oh, too tight, converges to 0. Okay? But the important part is, we don't need this parenthesis, to figure out what is the common ratio. 3/7. And you may, yes, you may finish this solution like this, but we can compute a limit. What we can do? Okay, algebraically, like I can combine, right? I mean, I can maybe rewrite here, -3 and 7, everything is taken to the power of n. And that's obvious that that number is common ratio, but having this original form, it's maybe a little bit challenge, but I know that is relatively easy at this point for all of us. Okay, but I will probably keep this form. Okay, I will keep this form because this one will be nice, will let me to apply the absolute value since I see the -1, I see the alternation. Absolute value will change the formula a little bit. -1 to the n will become positive. 3 to the n is positive, then will stay the same. 7 to the n is positive, will stay. And this one is definitely 0 because, yeah, denominator is winning, or 3/7 is the common ratio. 0. If the absolute value is 0, then the original sequence is also 0. Limit, of course, at infinity is also 0. This is the tool that we use, the property we remember. If the absolute value of the sequence, if that limit will be not 0, then that tool is not helpful. We have to find a different way. Okay, this sequence converges to 0. And another one, okay, let's look at this. Of course, I will repeat, looking at the formula, I investigated really quickly that all of the n's, n is infinity, are placed in the exponent. Then this is the geometric sequence. Yeah, no expanded form, no addition, subtraction. This is just the geometric. Now I have to figure out what is the common ratio. And what we see? We see -1 to the n. We see 2 to the power of 3, which is 8. 8 to the n and 5 to the n. -1, 8, and 5. That's the common ratio. Yeah, please practice this. I will write down everything, but I really would like my students to figure out the common ratio almost right away. Yeah, because 2/3. Yeah, where that 8 come from? Because this is 2 cubed, -8/5. This number, unfortunately, is outside the interval. This number is less than -1. Oh, I am not planning this properly. -1 is taken to the n, 2 cubed, and 5. -8/5. This number is less than -1, is outside this interval. This sequence is divergent. Because it's negative, -1, it's negative, common ratio, it will alternate, but the terms will get bigger and bigger because this is the absolute value is greater than 1. Like we remember, every other term will go to the positive infinity, every other term will go to the negative infinity. Okay, that's almost done, but with respect to the limit, yeah, we can say -1 to the n. I just want for some of us maybe to figure out what is the common ratio. And that means I will say -1 is taken to the power of n. This is taken to the power of n, and 2 is also taken to the power of 1. Yeah? Because when we adding exponents, we can multiply the base. 5 is taken to the power of n, and 5 is taken to the power of -2. And then I can combine -1, 2 cubed, and 5 in the denominator. All of these quantities are taken to the power of n. And then we have 2 and 1/5 squared, which is 25. Oh, I'm taking -8/5 taken to the power of n, and this will be 50. Yeah, because this is 1/25. Dividing by fraction means multiplying by the reciprocal, 2 times 25. Okay, that means this is a good form. We can see we did the blue formula, the original form, we did change to, this is also blue. Okay, we can definitely see the common ratio. And having this form, I can say right away that the limit of -8/5 to the power of n, this is telling me that this will go to positive negative infinity, every other term, then I can say the limit does not exist. Or if we will take absolute value of this will be infinity. If it's infinity, we're not using that actually property. Okay, the limit is undefined. If the limit is undefined, the sequence is divergent. Yeah? And we can say this, but that's not a good, that's just my thinking. Every other term, yeah? Because this number 8/5 is greater than 1. Okay, I think we did a lot. What I have, I have the list of the sequences which you can try to solve. You should be able to actually do all of them. But if I have to ask you which one is the geometric one, okay, you will like tell me, okay, not the first one, not the second one because of n. Oh, this is the geometric. This one, number 4, has n in the exponent, but also has n here. That's not a geometric. Number 5 is definitely not the geometric. Number 6, n in the exponent, n in the exponent, n in the exponent. That's the geometric. 7 is not the geometric. And 8 is like a combination, but it's not a geometric because we have addition. And this will be 1/e to the n, like 1/. Yeah. So I mean, this one we can just look at it is part of this is the geometric, but not the entire sequence. You can see this is the common, I mean the leading function, e to the n, 2, 4, we know the limit. Okay, but this one of course is divergent. You can tell this. And this one is also divergent. And you can figure out why this is divergent. Yes, 16/9, 16/9, and even negative 16/9. Greater, the number outside the R. The common ratio is this. The common ratio is 9/4. Greater than 1, less than -1. That's not what we need. Thank you. Enjoy your geometric sequence.